Right, suppose we have three particles and they are constrained to move on this ring, and they're also, they have to stay fixed. So maybe I should draw a triangle here. I don't know, just to show that they stay fixed. So they, with respect to each other, meaning they will stay equally spaced around this ring, even though they're able to rotate around the ring. So let me just draw an arrow like this. All right, so they all stay, 60 degrees or 2 pi thirds away from each other as far as the angle is concerned. And also they obey Bose statistics. So the wave function will be symmetric under particle exchange. So what we want to do is look for any restrictions on the magnetic quantum numbers, so just the m quantum numbers, so for rotation around this axis. So let's just, anyway, we'll just call this the z-axis that they're rotating around. So, okay. And we'll also want to learn about the energy levels of this system. So, so I guess first to look for restrictions on the magnetic quantum numbers. So one thing we know for bosons is when you exchange two of these particles, the wave function has to remain the same. So let me just write the wave function just as one ket here. All right, so say we had an operator, we can call it a permutation operator, and let's see what we can do here. Let's exchange particles 1 and 2, and then let's come along and exchange particles 2 and 3. Okay, so so for bosons, this permutation operator, the eigenvalue is just going to be 1. So this is going to be equal to exchanging just particles 2 and 3 or basically just the original ket. All right, so as each of these act on this ket, we just get an eigenvalue of 1. All right, so but the reason we're using 2 of these, well, let's just draw it out real quick. So after we permute 1 and 2, the first case, what we now have, 1 and 2 are switched. So now 2 is here and 1 is here. 3 is still here. Okay, and then the second permutation we're doing is permuting 2 and 3. So now 1 stays here, and 2 is going to come down here, and 3 is going to go up here. Okay, so the reason we use 2 of these here is just to show that the wave function is unchanged under these 2 permutations, which is identical to the case if we had rotated this by 2 pi over 3. So if we had 2 pi over 3, I'll just call that angle phi, rotation. Then what happens is 1 is going to come down here. So 1 comes here, 2 comes here, 3 comes here. So 1, 2, and 3. And these 2 cases are equivalent. All right, so we found that the eigenvalue for using these 2 permutations is 1. Since these 2 are equivalent, we get some restrictions on the eigenvalue for our rotation operator. So our rotation operator is similar to the time evolution operator, or propagator. So for a rotation, we have e to the minus I LZ phi. I'll put a little subscript on this because anyway, normally there's an L dot phi or whatever for an arbitrary type of rotation, but we're only going around this this z-axis. So let me draw that coming. Okay, maybe it should be going into the page or something. Anyway, we're rotating around the z-axis. So anyway, the rotation operator, so we have this I, LZ, phi, and then divided by h bar. All right. So now we're going to put this onto our ket, right? And when this phi z is equal to 2 pi over 3, or multiple of it, right, as we move around, then we should get an eigenvalue of 1. So whatever the eigenvalue for the general case is, if we go a little bit more specific here, and we have an e to the minus I L z, and now plugging in 2 pi over 3, okay, that acting on the ket, this eigenvalue will give us a 1. So we just get this back. All right, so that's all this was designed to show us, is that this rotation operator with this this angle plugged in, we get this case, right, the rotation, that's equivalent to using these two permutation operators, and we get the same eigenvalue. All of this comes down to e to the, oh, you know what, I guess I can, yeah, I'll write this out a little bit better. Okay, minus I L Z 2 pi over 3 h bar, because what I should do is apply this LZ operator to this ket. So this is the only quantum number in this operator, so we don't have to worry about commutation or whatever. We can just put the eigenvalue of this operator right in here. So for what we have, all right, so we have a minus I, so LZ returns an m h bar. I'll put the m here, sure, 2 pi, and then the h bar is going to cancel with this h bar down here, so we just have a 3 downstairs. All right, and then so we have this sort of middle case here, but this has to be equal to 1. Okay, an eigenvalue of 1 right here. Okay, so again, extra steps, but we have 2 pi over 3 is equal to 1. All right, these eigenvalues match up. Okay, so for this complex exponential, this will be equal to 1 whenever 2 pi m over 3 is equal to some integer multiple of 2 pi. So I'll just use n for that, so where n is an integer. If that works. Okay. All right, so now if this equation holds true, then m equals 3n. Right, we cancel the 2 pi's, multiply both sides by 3, we get m equals 3n. So this is our restriction on the magnetic quantum numbers. So here's our magnetic quantum number, and for this this LZ rotation, or I guess I could use a J here, right? It's just a general rotation. I don't have to use L. Okay, so it must be an integer, which is a multiple of 3. So now looking at the energy, so normally for energy we have momentum squared over 2m. This is in the rotational case, we have L squared over 2m, but here we only have rotation in the z direction. So this is just going to be, I guess, we only have rotation of about the z-axis. So this will just be an Lz squared. And then instead of m, we get I, where I is the moment of inertia. So this is going to be our Hamiltonian. Okay, so applying this to our state, okay, LZ, again, we get mh bar, except now it's squared. And then 2, okay, and so for I, another thing I forgot to write is each one of, let's use a big M for the mass of these particles. That way we don't get it confused with this little m. So that's just going to be, there are 3 of them, m r squared. Another thing, of course, forgot to write, this circle will have a radius which we'll call big R. All right, so a few minor details we forgot here. All right, so this is just the eigenvalue. We still have our ket right here. So this tells us that E n, so for the nth eigenvalue or level, we get an m squared h bar squared over 6 big M r squared. And we notice there's no n in this, right? Only our m, or little m. And so now we go back to the restriction we found for our magnetic quantum number, and we get 3n. So 3 squared is 9, n squared, h bar squared, 6m. This is big M, r squared, or 3 over 2. All right, so there we go. So here are the energy levels of this rotating system for these 3 equally massive bosons rotating around this ring while staying equally spaced. All that great stuff.